Welcome to the solution to the AP Measurement and Vector Analysis problem set, problem number 8. In this problem we have the helicopter view of a picture showing two people pulling on a stubborn mule. The forces are measured in units of newtons. Find, using the method of rectangular components, A, the single force that is equivalent to the two forces shown, and B, the force a third person would have to exert on the mule so that the net force on the mule is equal to 0. Alrighty, so I've started off with here, you got your picture up here in the top right hand corner, but I've sketched these forces out on the rectangular coordinate system, and the first thing that we want to do is generally establish where our resultant is going to be. To do that, what we draw is called a parallelogram. It's the parallelogram method of solving for a resultant. So what we want to do is we want to take this vector equal magnitude and equal direction, and we want to attach it to the end of the 80 Newton vector. And then we want to take the 80 Newton vector and attach it to the end in the same magnitude and same direction to the end of the 120 Newton vector. And here we have our parallelogram, and the resultant ends up being the diagonal of that parallelogram. This is a very common method when you have two or more forces acting concurrently on a point. You would use a parallelogram to find the resultant. Now these aren't necessarily drawn to scale, and you wouldn't be drawing this to scale either. You're doing this as a rough sketch. But what this does is it gives you a general idea of where is your resultant. We see that it's in the first quadrant, and it's generally closer to the positive y-axis than it is to the x-axis. The reason we're doing this is because our answers that we get should match or be consistent with this type of thought that we have here with regards to what the solution should be. All right, so let's proceed. We're going to go ahead and label this. This is F1, which is our 120 Newton force. It's at 60 degrees. Okay? I'm going to go ahead and label that. And we have F2 over here is 80 newtons. And it's at 75 degrees. But remember my little tip here. If you use 75 degrees, fine. But if you do that, make sure you pay attention to your signs for your x components and your y components. What I'm going to do instead is I'm going to use the angle on the rectangular coordinate system here. So this is 105 degrees when I go to do my calculations. 180 minus 75. Okay? All right, everything's pre-labeled here. Let's take a look at what we're going to do. We're going to need to find the x component, which is in red here, and the y component, which is in green, of our F1 vector. And we need the x component, also in red, and the y component there in green. Okay? All right. So now that we have our right triangle sketched out, we're going to go ahead and set up a chart. Okay, so the chart will look something like this. We've got force for a heading, x component, y component. Keep our information all organized. We have forces F1, force F2, and of course our resultant. And of course the reason we're doing this is because we're looking for Rx and Ry, so that we can end up using Pythagorean theorem to find R, and we can also use the tangent function to find the angle of our resultant as well. All right, so here we go. Let's start off with F1, the x component. We're going to use the x component is adjacent to the 60 degrees, so we're going to use cosine. So we have 120. Cosine is 60 degrees. Cosine of 60 is the same as the sine of 30. 1/2 of 120 is 60 newtons. Okay? Let's do all the x components first this time. Over to F2 we go. We've got 80. Cosine of 105 degrees. And that gives us a value of negative 20.7 newtons. Now if you use the 75 degrees, that's fine. Just remember that you have to assign it the negative value because it's in the second quadrant. Y components, 120. Sine, because that y component is opposite the 60 degrees. Sine of 60 degrees, and then equals 103.9 newtons. F2, 80, sine of 105 degrees, and that equals 77.27 newtons. Notice how we're carrying digits out further than what we need to, because we don't want to sig fig ourselves out of the correct answer here. All right, so now we go ahead and we add our x components to get our resultant x component. And so we've got 60 newtons minus 20.7 newtons. Same thing. And we should be getting 39.3 newtons when we calculate that. And then we've got, for Ry, we've got 103.9 newtons plus 77.27 newtons for a total of 181.17 newtons. All right. Now up here on the diagram, okay, let's just double check and make sure our answers make sense. Should we have an x component that's positive for our resultant? Yes, because its x component, as indicated in the dashed blue arrow here, is in the first quadrant. It's on the positive x-axis. Our y component for that resultant would be on the positive y-axis, so we should have a positive y value, and it should be longer than our x value. Everything looks good so far. Okay? So here's our rx, and here's our ry value. All right? We can now go ahead and calculate the value of the resultant itself using our trig, since those components are perpendicular to each other and form a right triangle with the resultant itself. So r squared equals rx squared plus ry squared. R squared equals 39.3 squared plus 181.17 squared. Add the squares, take the square root, and we get 185 newtons. Okay. Our angle of our resultant, our direction, is the inverse tangent. Just a little hint for you here, if we're always measuring it from the x-axis, it's always going to be the y component over the x component, opposite over adjacent. The inverse tangent of that, calculated 77.8 degrees. Our final answer, R, the resultant, is 185 newtons at 77.8 degrees to the positive x-axis. Let's go back up, see if that makes sense. And it certainly does seem to match what we sketched out as a rough diagram there. That's the answer to A. Now, B. B wants the single force of the third person would have to exert on the mule so that the net force on the mule is equal to 0. Well, where would a third person have to pull so that the forces cancel each other out? Well, it would have to be in the, they would have to pull the same magnitude that we calculate for our resultant, but they would have to pull in the opposite direction. In other words, this vector shown here is the same magnitude of r, but in the opposite direction. That vector is given a special name because it creates a situation in which our system is in equilibrium, and that is called the equilibrant. The single force that keeps a system in equilibrium is called an equilibrant. That's what they're asking you to find in 8b. So the answer is pretty easy. It's got to be the same magnitude of the resultant, so it's 185 newtons at what's opposite direction in angle talk? Well, that opposite direction would be 180 degrees to the resultant. So to express our answer, we simply take the angle of our resultant and add 180 degrees to that answer. When we do that and take our 77.8 degrees and add 180 degrees, we get 257.8 degrees, which matches because that's in the third quadrant. All right, so this is a neat problem using the method of rectangular components, and we'll have another one of these to do in class.